Hello to everyone. Today we are going to learn some new concepts in the as a part of lecture 3, that is condition number of the polynomial roots. So if you quickly recall the last lecture, we did finite digit arithmetic, how actually the rounding and chopping can be taken place when you are doing the numerical calculations to get the desired accuracy. So as you know very well, the condition numbering is very important while trying to find out these numerical solutions to the system of equations. And then for example, when you have a polynomials, then you want to find out the polynomial at different values of x. So what is the best way, that how do you get the best approximation? So in that case also we use what you call the condition number. So let us see the problem of finding roots of a polynomial can be highly ill-conditioned. As we know very well, when the system is ill-conditioned, then we will not be able to get the desired solution. So it becomes very difficult for us to find out a solution to those polynomials. Let us take some simple example. Let fx is equal to x square minus 2x plus 1 is equal to 0. So all of you knowing this is a quadratic polynomial. Now as you know very well, the roots are 1 comma 1, repeated roots. So because fx is equal to x square minus 2x plus 1, so you can write it as x minus 1 whole square. So therefore x is equal to 1 and x is equal to 1. So that means you do have a repeated root. Now perturb the coefficient 2 in the polynomial by 0.00001. Okay, so now let us perturb the polynomial by 0.00001. The computed roots of the perturbed polynomial, so I call it as f cap of x. So f cap of x, it becomes x square minus 2.00001 x plus 1. Okay, so therefore for this equation, so you do have the roots, that is, this is the x1 and this is x2. So if you observe very closely, the roots x1 and x2, see that here 1.0032, okay, instead of 1, and second root is x2 is equal to 0.9968 instead of 1. So just with small perturbation in the coefficient, the solution actually, it goes to 1.0032 and x2 is equal to 0.9968, which is much different from the true solution. So if you compute the relative error, see that here relative error, so x1 and x2, let's say, are 0.0032. So this is the relative error. The relative error in the data is 5 times of 10 power minus 6. So therefore, we can make a conclusion that thus a small perturbation in the data changed the root substantially. So that means the system is very sensitive system. So if we have a sensitive system, it becomes very difficult to handle. So therefore, in many of the realistic situations, you do get very sensitive systems, although the changes are very minutely small. So maybe 10 power minus 6 or 10 power minus 8, etc. But then the system actually changes substantially. So therefore, one should be very careful about how actually you should handle such a system when you have these kind of problems. So therefore, not only just it is a quadratic, in the real life cases, you do have the fourth degree or fifth degree, even higher degree. So therefore, the higher the degree of the polynomial, the change in the roots will become much and more. So therefore, you do get a high level of relative error. So therefore, one should be very careful in handling such systems. Next, let's see what is the remark over here. The condition number is data dependent. So therefore, the condition number is data dependent. So that means if you have the data is not very proper, or maybe you do have a very unusual data. That means you may have a evenly spaced, or you may have a oddly spaced data. So if you have this kind of data, then what would happen is it would be very unlikely to find out solution to such systems. That means the condition number is data dependent. Thus, a problem which is ill-conditioned for one set of data could be well-conditioned for another data. So very interesting here. You see here, for example, I have some matrix system. Okay, this is the coefficient matrix and this is the unknown vectors. Let's say this is the right side vector. So if you have such a system and one problem may be ill-conditioned for some data, and it could be well-conditioned for the same data which I have considered for the ill-conditioned system. So therefore, so essentially I can make a conclusion that the condition number, although it defines the stability of the system, right? So it is data dependent. So therefore, the condition number of a problem is a property of the problem itself and has nothing to do with the algorithm used to solve the problem. So you may have a different algorithms. You may have a Cramer's rule, you may have a matrix inversion method, you may have a eigenvectors, you may have a what you call this, the Ax is equal to B quadratic forms, you may have a singular value decomposition, so on and so forth. But the condition number of a problem is a property of the problem itself. Okay. So, and has nothing to do with the algorithm used to solve the problem. So, this is a very worth noting point. So, therefore, it is a data dependent and it does not depend upon the what algorithm you have been using to solve this problem. Okay. Next, another remark we can also make a note of it is the accuracy of the computed solution by a given algorithm. The accuracy of the computed solution by a given algorithm is directly connected with both the stability of the problem and accuracy of the problem. So that means you do the accuracy will be dependent on given algorithm is directly connected with the stability of the problem and accuracy of the problem. So accuracy, as we see, we want to have a 4-digit arithmetic with rounding or 5-digit arithmetic with chopping or something like that. So it also defines how best the solution is. Similarly, the condition number also, it defines, it gives us the stability of the solution. That means we would be interested in both stability of this problem as well as accuracy of the problem, so that we should be able to get the best approximation, right? Okay, this is very worth noting, right? So that means we wanted to have stability plus accuracy, which will give you the best approximation, So that means you do have the solution which will be stable. So stability, already we have seen that the condition number should be a very small value, condition number. So as the condition number is becoming bigger and bigger, it would be far away from the stability, right? Similarly, accuracy, which we have seen that you do want to have a best accuracy, that is 5-digit arithmetic, 4-digit arithmetic. That means the relative error which you have computed would become smaller and smaller. That's the idea, the stability and the what you call the accuracy. Now let us take this ill-conditioned. For ill-conditioned problem, no matter how stable the algorithm is, the accuracy may not be guaranteed. The accuracy depends upon the condition number. You see, they are all intimately connected. Accuracy, they are all accuracy, comma, stability. Accuracy, comma, stability. So, the accuracy may not be guaranteed. The accuracy depend upon the condition number. How better you are going to have the condition number. So therefore, that means the stability would be almost, it would be captures the accuracy the way the definition looks like. That is, the for ill-conditioned problem, no matter how stable the algorithm is, the accuracy may not be guaranteed. The accuracy depends upon the condition number. So that means essentially, if you catch hold of the stability, many of the problems would get settled. So therefore, it is a very, very important problem. And to know the stability, and you need to compute the condition number. Okay. Should I go ahead? Yes. Next, we can make a conclusion that accuracy depends upon condition number. So again, you see here very clearly we are writing it as accuracy depends upon the condition number. Stable algorithm, backward error, that is what is called backward error. That means you do have a y prime minus x prime, okay, minus x prime. Okay, so what is that? Y is equal to fx. So y prime is nothing but the function evaluated at x prime. So that is the backward error. So stable algorithm is backward error plus well conditioned. So if these two holds, accurate solution, the computed solution is near the exact solution. You do have it. So stable algorithm plus well conditioned, it will give you accurate solution. Stable algorithm plus accurate solution, it will give you stable algorithm. So stable algorithm plus ill conditioned problem will be accuracy not guaranteed. Stable algorithm, if you have a stable algorithm and then the system is ill conditioned, then you may get the better accuracy or you may not get the accuracy. That means it is not guaranteed. It is not guaranteed. So the conclusion is the following: stable algorithm, that is backward errorless plus well conditioned problem, that will give you accurate solution. That is, the computed solution is near the exact solution. And stable algorithm plus ill conditioned. So if I have to have a will condition, then the accuracy may be or may not be. That is, may be or may not be. Maybe or may not be. So this is not guaranteed. Okay, so having had this condition number, let us go ahead. What is the answer inaccurate? Very interesting question. Let us see what is the answer inaccurate. So it will have, maybe the problem might be ill conditioned, right? Whenever you are getting the inaccurate solution, inaccurate, right? The problem may be ill conditioned, algorithm might be unstable. So either way we can define. So that means the inaccurate means the problem may be the problem might be ill conditioned or the algorithm might be unstable. So in either cases you do get a inaccurate solution. So therefore we wanted to have a well conditioned system. But unfortunately, you see, in many of the realistic situations, the physics of the problem forced us to model ill-conditioned system. That means, how do you bring this ill-conditioned system into a well-conditioned system so that you could able to get stable algorithm. So when you get this stable algorithm, it will lead to what you call the stable solution. Why is the answer inaccurate? The problem might be ill-conditioned. The algorithm might be unstable. So in either cases, you do get what we call the inaccuracy. Now, let us look at into the issue of perturbation. So, let's say that we have a system x1 plus 2x2 is equal to 3. 2x1 plus 3.999x2 is equal to 5.999. So what is the exact solution for this? So exact solution we see x1 is equal to 1, x2 is equal to 1. This is the exact solution. Okay, because when you substitute here, x1, 1 plus 2 is equal to 3 and 2 plus 3.999 is equal to 5.5. So this is the exact solution. Now let us perturb the coefficients of this equation. Now when you perturb the coefficients of this equation, let us see how it looks like. Look at this. Now make this small perturbation on the RHS. So what I did is x1 plus 2x2 is equal to 3. That is fine. Second equation is 2x1 plus 3.999x2 is equal to 6. Okay, so this is different from what we did earlier. By Gauss elimination with partial pivoting, we have the roots like this. That means x1 is 3 and x2 is equal to 0. Okay, by using the Gaussian elimination with partial pivoting. Okay, thus small change in the RHS changed hugely in solution. That means there is an enormous amount of change in the solution. You see, the initially it was x1 is equal to the one which we wrote, x1 is equal to 1 and x2 is equal to 1. So x2 is equal to 1. You see here x1 is turns out to be 3 and x2 turns out to be 0. So that means there is a huge change in the solution. So what is the remark we can make it here? The sensitivity of this linear system is measured by the condition number. So condition number will measure the sensitivity of the system. So therefore, one has to be very careful while giving the perturbed solution. By the way, why do you want to have a perturbed solution? Because many of the race situations which you get in the day-to-day life, the coefficients are very sensitive. Therefore, we are forced to handle such systems where the sensitivity of the solution is very important. Now let us look at into the another issue, effect of perturbation on the RHS of the vector B. Look at here. Assume impurity in B, but the matrix A is exact. So I shifted this matrix A to A. B, I just did it as B plus delta B. What is delta? Delta is nothing but small change in the perturbation. And x is also x plus delta x, change in the solution of the x, and this is the perturbed in B. Now the question is how to find out a solution to this system when the perturbation takes place on the RHS of the vector B. So it is very interesting. Let us look at the, before handling that, let us do have some theorem. What is this theorem? This theorem says if delta B and delta x respectively the perturbation of B and x in the linear system Ax is equal to B, A is non-singular and B not equal to 0, then you see here the norm of, okay, so that means delta of B upon norm of A inverse. Okay, this fraction is less than or equal to delta x norm upon norm of x, and which is less than or less than norm of A times of norm of A minus multiplied with delta of B upon norm of B. So you see here, so very interesting theorem this is. If delta B and delta x are respectively the perturbation of B and x in a linear system Ax is equal to B, A is non-singular and B not equal to 0, then delta of B upon norm of A times of norm of A inverse will be less than or equal to norm of delta x upon delta x is less than or equal to norm of A times of norm of A inverse multiplied with delta B upon B norm. Okay, so now let us look at into the solution, how we could able to find out the solution to the system. So the proof is very simple. Let us start with Ax is equal to B. Okay, and x is x plus delta x. That means A times of x plus delta x, A times of x plus delta x. This will be equivalent to b plus delta of b plus delta of b, which implies I can write this as a times of delta x is equal to delta of b. So that is, we can write this as delta x is equal to a inverse of delta of b, because the matrix A is assumed to be A is non-singular. A is non-singular. That means inverse exists. So therefore, this is very important theorem. That is, since Ax is equal to B, so replace this x by x plus delta x. So it will be equivalent to B plus delta B, which implies A delta x is equal to delta B. That is, delta x is equal to A inverse of delta B, since A is non-singular matrix. Now let us look into the norm in terms of norm. Okay, delta x, norm of delta x is less than or equal to norm of A inverse times of delta B. Let's say this is the equation 1, which implies delta x upon, just push this delta B norm to the denominator. So that means you do get the inequality norm of delta x upon delta B less than or equal to norm of A inverse. Also, norm of Ax is equal to B, also norm of Ax is equal to B, which implies B is equal to norm of Ax, which is less than or equal to B is equal to norm of Ax, which is less than or equal to norm of A into norm of X, and which implies 1 over norm of X is less than or equal to norm of A upon norm of B. So that means you do have a equation 1, you do have a equation 2. You see, from these two equations, what we can make a conclusion is, we can make a conclusion that from 1 and 2, you see here, norm of delta x upon norm of x, norm of delta x upon norm of x, which is less than or equal to norm of A times of norm of A inverse multiplied with delta B upon norm of B. As A times of delta x is equal to delta V, as A times of delta x is equal to delta V, which implies delta x is greater than or equal to delta B upon norm of A. So this is, I call it as equation 3. Also we have Ax is equal to B, so 1 by norm of x is greater than or equal to this thing, I call it as equation 4. So from equation 3 and equation 4, I can make a conclusion that norm of delta x upon norm of x is greater than or equal to norm of delta B upon norm of x multiplied with norm of A inverse of norm of B. Well, now let us go ahead with simple example. You see this example, let us start with ill-conditioned system, right? You see here the entry is very small, 4.0001, and this is 2.002, this is 2.002, this is 2.022. Let's say right side you do have a 4, 8.0021, 5.006, and as you know that this exact solution turns out to be 111. This is the exact solution. Let us handle this system in more systematic way. Let us change this matrix to a new matrix. The previous matrix, whatever you have it, change this matrix to a new matrix. That is new matrix. Wanted to change to a new matrix. What is the new matrix? So new matrix will have the elements for 8.0020, 5.001. So I change this matrix. That means your system Ax is equal to B. So I call it as a B prime because the contents are changed. So I call it as a B prime. So that is, this is, we call it as a B prime. Okay. Now let us look at into the analysis, the one which we did it, relative perturbation here. So when you talk about the relative perturbation, the norm of B prime minus B upon norm of B. So which will be equivalent to norm of delta B upon norm of B. So which will be norm of, so this is for 8.0020, 5.0061, that is fine. minus this B 4 and 8.0021 5.006. Okay, and when you take denominator you will have again 4 8.0021 and this thing. So from this we can write it as in this form, that is norm of 0 0.0001 0.00001 upon this norm of this is 4 8.00021 5.006. So we can write this as 0.00001 upon 8.0021. So this can be written as 1 into 10 power minus 4 upon 8.0021. So this will be equivalent to 10 upon 8.0021 multiplied with 10 power minus 5. So this turns out to be 1.2498 times of 10 power minus 5. So in fact this is very very small value, very smaller value. Okay, so this kind of smaller value, how can you find out a relative perturbation for this? Well, so if you solve the system Ax prime is equal to Bx B prime, then we get the perturbed solution x prime is equal to x plus delta x. So delta x is the small perturbation. Okay, so having had this ground, let us now quickly go into the importance of the norm. How do you compute the norm and what are the kinds of norms you do have in the numerical computations? So very familiar norms are 1 norm and 2 norm, infinity norm. Let us take very simple example, 3 by 3 matrix. So it is a 3 rows, 3 columns. Let's say that. What is the 1 norm? 1 norm is, I denoted it as 1 norm. So that is norm of A. Maximum of minus 3, this element, 2, 0, or maximum of 5, 6, 2, addition of this, maximum of 7, 4, 8. So that means essentially maximum of this or maximum of this, maximum of this. So this turns out to be 3 plus 2, 5, it is fine. 5 plus 6, 11 plus 2, 13, and 7 plus 4, 11, it is 19. So the maximum value is 19. So therefore we can write it as 1 norm. 1 norm is equal to 19. 1 norm is equal to 19. So that is fine. Now similarly, let us look at into infinity norm. So what is the infinity norm? Infinity norm is maximum of minus 3, 5, 2, comma 2 plus 6 plus 4, 0 plus 2, 8. So this is 5, 3, 15, 15, right? 5 plus 3, 50, 5 plus 3, 8, 8 plus 7, 15, 2 plus 6, 8, 8 plus 4, 12, 2 plus 8, it is 10. So maximum of this is 15. So in the previous case, you see infinity norm is 15, whereas 1 norm is 19. So in this case, 1 norm is higher than the infinity norm. There is a very popularly we use what we call Euclidean norm L2. Is the matrix is the spectral norm. We call it as a spectral norm. So norm of A is nothing but, so lambda of maximum A star multiplied with A. A star multiplied with A. This is what is called Euclidean norm. So norm of A2 is lambda max A star of A. Well, this is a quite popularly we use in the analysis of, the differential equations and functional analysis and many more areas. Now let us get back to the well conditioned system, because we were talking about the condition number, ill conditioned, well conditioned. So we should get familiar about how the system looks like and what are the instances to find out a better approximations. A well conditioned system. Look at here, this is the coefficient matrix, this is the matrix B. The exact solution turns out to be 1, 1. Now let us perturb this B to 3 plus 0.00001, 7 plus 0.00001. So if you use these two things, you do get what you call 3.0001, 7.0001. Now this is a well conditioned system. So if the system is well conditioned, it is well and good, we do have a solution. But if there is a small perturbation like this, then what would be the nature of the better approximation? Well, well, look at into the relative change in B. So what is the relative change in B? Relative change in B is the norm of B prime minus B upon norm of B. So this is the relative change. So if we compute this, it turns out to be 0.0001 upon 0.0001. So 3 comma 7. This is the norm. This is the norm. And here it is 001. This is fine. And the maximum value is 7. So it turns out to be this thing. Multiplied with very small number, so therefore 0.001 by 7. So if you write it as 7, so it is 1 into 10 power minus 4 upon 7. Again I write it as a, so like this, so it would be 10 power minus 5. Okay, so it is a not 15, it's 10 power minus 5. Very small number you do get into this. So therefore it is very important to find out the relative change in the errors. So therefore relative change in the errors will be calculated based on the norm. Well, let us go ahead. Condition number. So as by definition, already we spoke, the condition number is nothing but norm of A times of norm of A inverse. So what is the A inverse for the matrix? A inverse, you know, this is 1 by determinant of A times of the transpose of cofactor matrix. Transpose of cofactor matrix. So if you have a transpose of cofactor matrix, then you do get what we call A inverse, and maximum row sum is A inverse of 3, and in the previous case it was 7. So 7 multiplied with 3 is 21. So the condition number is becoming a 21. Okay, so now what is the conclusion you can draw from this condition number? As already we spoke, the condition number will decide the stability of the system. Well, having had this definition, the condition number is a bigger number, it is a 21, so therefore it will lead to a what you call unstable solution. Now you do have a what you call the condition number. So condition number is A times of, you will have norm of A times of norm of A inverse, which is 21. Okay, fine. So 21 is a bigger number, so it will lead to a unstable. Let us see x prime. So x prime is 0.9999, 1.0001. Okay, this is the true solution is 1, 1. So note that delta x upon norm of x, so which will be equivalent to 10 power minus 5. So which is very small. Fine. In the previous case also, which we calculated, it is 10 power minus 5. 10 power minus 5. Well, now what is the remark over here is the condition number decides the sensitivity of the solution. The condition number decides the sensitivity of the solution. Well, let us make the broad conclusion. If the condition number is not too large, that means greater than let's say 100 or bigger number, then a small perturbation in the vector B, will have very little effect on the solution. On the other hand, if the condition number is large, then even a small perturbation in B might change the solution drastically. The system Ax is equal to B now is said to be ill-conditioned if the condition number A is too large. That means you see here 10 power 5, 10 power 8, 10 power 10. So in the previous case it was only a number is 21. We can call it as a small number in compared to this number. So that case we can conclude that that is a stable system. Okay, fine. Yes, so the system Ax is equal to B is ill-conditioned if the condition number A is too large, that is 10 power 5, 10 power 8, 10 power 10, etc. Otherwise, it's a well-conditioned system. Now, let us see this example. A is equal to, let's say this example A is equal to, we will have 1, 0, 0, 0, 1.999 and this is 0.9991. Now, what is the A inverse for this? A inverse is, I do compute this A inverse as 1 over 1.9999 squared. So this is multiplied with this matrix. So it turns out to be 1 minus of 0.9999 minus of 0.991. So which turns out to be this. So that means 10 power 3 multiplied with 5.0003 minus 4.9997 minus 4.9997 5.0003 upon computation. So therefore, you can see from this example, the values are very small values, A inverse. Now let us look at into the norm of this. So norm of A infinity is maximum row sum. When you calculate maximum row sum, it turns out to be 1.9999. And when you calculate the one norm, maximum column sum. So that is infinity norm is maximum row sum. That is one norm is maximum column sum, which is 1.999. And what is the A inverse infinity norm? A inverse of 1, which is 1 over 10 power 10. And the condition number is nothing but norm of A times of norm of A inverse. Condition number is, that is A1 times of A1 of inverse, which turns out to be a very bigger number. So that means it will leads to unstable system. It will leads to unstable system. So it becomes very tricky how actually the bigger or smaller. So that means in the previous case what we did was 1521 is okay. So that is a small, we can call it as, compared to this number, so that is very small. So in this case it is unstable, and in the previous case it was a stable system. Well, now let us go ahead. The condition number with respect to 2 norm. So when you talk about 2 norm, norm of A2 is row of A, which is equal to norm of A2 is row of A, which is equal to the square root of lambda max times of A inverse A star times of A, and which turns out to be norm of A2 is 1.9999. And a norm of A inverse of 2 is square root of rho times of A inverse, which turns out to be 10 power 4. Therefore, we can write it as condition number of A is nothing but 1.9999 times of 10 power 4. That is, norm of A, 2 norm is the largest singular value of the matrix. So norm of 2 is the largest singular value of the matrix, that is sigma A. Note that the condition number with respect to any norm is same. So in this case, you see here, with respect to 2 norm is same, with respect to infinity norm is also same. That means the condition number is same in some of the cases when you compute the large systems. Well, now let us look at into the example. Well-known ill-conditional matrix, all of you knowing very well, and this is the Hilbert matrix. So when you have a Hilbert matrix, you see contains 1, 1 by 2, 1 by 3 like this, you do have it, and you have a 1 by 2, 1 by 3 like this, you do have it. So this is the well-known Hilbert matrix. Now what would happen to the ill-conditioned property of this Hilbert matrix, right? So you see here, the n is becoming bigger and bigger, the value becoming smaller and smaller. So how do we handle such systems is the very important issue in trying to find out the ill-conditioned or well-conditioned. Now let's say if you start with say n is equal to 10, so n is equal to 10, let's say that. So if n is equal to 10, what is the condition number pertaining to A? So this is turns out to be, you know, when you calculate it, 1.6025 times of 10 power 13. Similarly, when you compute this with respect to infinity norm, it is 3.5353 times of 10 power 13. Similarly, when you do compute with one norm, it turns out to be this. So in all these cases, it is a bigger number. Okay, so therefore, obviously you can conclude that the system will become a ill-conditioned system. Now let us see the Van der Waals matrix. All of you knowing very well, this Van der Waals matrix plays a vital role in many engineering applications. What is the specialty of this Van der Waals? Where Aij is equal to Vi raised to power n minus j, Vi is equal to ith component, that is ith component. For n is equal to 5, so this is ith component. So if you want to compute the condition number for this, it turns out to be 2.6170 times of 10 power 4, which is a bigger value as compared to the 21 which we did it. So these kind of matrices arise in polynomial interpolations. So when you are doing this polynomial interpolation, quite often you do come across in engineering applications. So this condition number for Vandermonde matrices. Well, let us go to the another very important concept which we come across in many engineering applications. That is, as we started with the Gaussian elimination, that is Ax is equal to B, solved by transforming the matrix A to an upper triangular matrix, Gaussian elimination, followed by solving two triangular systems which we call it as upper triangular matrix and lower triangular matrix. So I do write it as A is equal to L into U, where L is the lower triangular matrix and U is the upper triangular matrix. So now we have to see very carefully what are the instances where we can write this matrix A as L into U, and what is the necessary and sufficient condition so that we could able to write the matrix A as the L into U, different properties. So it is not just that all the time we can able to write the matrix A as L into U. There are certain conditions. If the matrix is positive definite, then we can able to write the matrix in terms of two product of two matrices L into U. And if it is not positive definite, then there is no guarantee that we could able to write the matrix A as L into U, etc. Now, let's see that the eigenvalues of a matrix A are computed by transforming A first to an upper triangular matrix H, followed by reducing H further to a square matrices. What is the square matrices? So, when you do the iteratively, right, we do bring that as a Heisenberg matrix. By the process is what we call square matrix iteration. We'll see that how actually you can bring this matrix into a square matrices, so that we could able to find out the solution to the systems. Now let us see the general process of the Gaussian elimination. How many are there in this case? There are n minus steps because you have n rows. So n rows. So I start with n minus 1 steps. So if you take n minus 1 steps, a power k is equal to that becomes aij raised to power k. Okay, k is greater than or equal to 1. Now, what is the coefficient matrix? The coefficient matrix says A1 is equal to A11, A12, A13, A1n. So, second row is 0, A22, 1, A22, 2, like this is, and this is the pivot, and this is the pivot for second row, this is the pivot third row, this is the pivot for nth row. So, that means A11 should be free from 0. A22 should be free from 0. In general, ANN should be free from 0. Okay. Now, let us go ahead with this computation, which can be written as A of 1 is equal to 1, 0, 0, 0, etc. M2 is etc. M3 is etc. Multiply this matrix. These are called multipliers. So, M21 is free from 0. Mn1 is free from 0 for the first column. For the first column. Now let us look at into the further course of action. Step 2. Multiplied entry of A1 is M21. So this one. So that means this one and next this one. So I do it iteratively. So iteratively each row. Iteratively up to n minus 1 rows. I keep on doing like this process. So if I do this process, what it can be written as A of 2 is equal to this matrix. This matrix you do get this matrix. Now further, what is the kth step? Kth step is when k greater than 1. So I do have a multiplier m of ik is equal to minus of aik k minus 1 upon akk k minus 1. This is the multiplier. I do have it. So therefore I do have this multiplier. Now n minus 1 step, what you get is at the end of n minus 1 step, the matrix A minus 1 becomes an upper triangular matrix. So upper triangular matrix, I have got it. So this is the matrix which I get it just before the multipliers. Now further, if I do simplify that, I do get this matrix as like this, the lower triangular matrix as well as upper triangular matrix. Now let us see with simple examples. You have a matrix A. Look at this matrix 2, 2, 3, 4, 5, 6, 1, 2, 4. And this is a matrix you see. So I do make it this as 4 minus 2. I will make it as, then it is 2 minus 2. So these two becomes 0 and this is anyway, this is free from 0. So A11 is free from 0, A22 is free from 0, A33 is free from 0. This I achieved. So this is the multiplier and this is the multiplier. So if I have a multiplier, then I do have the matrix. The matrix is like this. So this is the multiplier, another multiplier. So ultimately I do obtain this the upper triangular matrix. That means the main diagonality before that it will be 0. After there are non-zero elements. Similarly, the lower triangular matrix you see here, and this is the main diagonal. Upper will be zeros. These are all non-zeros. So that means the matrix A can be written as the product of two matrices L into U. So that means whenever you are given the coefficient matrix, we can always try to decompose this matrix A as multiplication of two matrices L into U. L is called the lower triangular matrix and U is called the upper triangular matrix. But remember that the LU decomposition is always not possible. So if there are some conditions, if these conditions holds, then always we can write the A as L into U. Otherwise, not necessarily all the time you can make it as a product of two matrices. So today in this lecture we have learned how to find out the condition number and what are the examples, how to compute the absolute error and relative error, and what is the Gauss elimination, and how the system will become ill-conditioned, well-conditioned, and how you can write the product of two matrices L into U, the coefficient matrix. Okay, so in the next class we will go ahead in this direction with the Gauss elimination with the partial pivoting, Gauss elimination with complete pivoting, and then other related issues. So I will stop at this juncture. Okay, thank you very much for listening to the lecture patiently. Thank you very much.